Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing last time? I think we were discussing about the Kilonew-Fischer synthesis. In a Kilonew-Fischer synthesis, how the aldose can be increased by one carbon atom that we have described, we have learned what are the steps, sequential steps used, what are the reagents used so that we can, starting from triose to tetrose, tetrose to pentose, pentose to hexose, how it is prepared, how we can increase one carbon atom. So that method, well-known method, is known as Kilonew-Fischer synthesis. So suppose as a glyceraldehyde, which is one of the what we can call it a reference compound used for the synthesis of rest of the carbohydrates. And as we know that carbohydrates means what? Carbohydrates are polyhydroxy aldehyde or ketone, or the compound which gives rise to a unit on hydrolysis is known as a carbohydrates. And in a Kilonew-Fischer synthesis, first one, it is treated with hydrogen cyanide. When that aldose treated with hydrogen cyanide form the derivative, the name of that derivative is cyanohydrine. And there are the two possibilities, two possible products are formed, and there is an addition of one new chiral carbon atom generated, and therefore, and after that, this cyanohydrine easily hydrolyzed by using the barium hydroxide. It is one of the reagent used to oxidize that cyanide group or hydrolyze that cyanide group into the carboxylic group, and that carboxylic group further required a heat. By providing heat, it produces the lactone is a derivative. And when the ester, and as we know that the ester, when open chain esters are there, we can call it as a ester. The general formula of ester is R C double bond O R dash. When that ester like the structure, when it is present in the ring form, that organic compound is known as a lactone. So lactone is formed depending upon the number of carbon atom present in the aldose, and that lactone will be treated with suitable reducing reagent. Generally sodium amalgam gives the aldehyde back, that ring get lactone ring get open, and there is a addition of that one chiral center or increase in the one carbon atom in the carbohydrates. So that lengthening of that carbon chain in the carbohydrate, that process is known as a Kilonew-Fischer synthesis. And this Kilonew-Fischer synthesis we have learned with the help of examples. So let us see the today what we are going to learn. Look at here, we are talking about the basics of carbohydrate. Exactly reverse process we are going to learn here. We are going to discuss today here. What is that? That is known as a rough degradation. Remember, rub degradation, it is also as a rub degradation. Rub degradation, and rub degradation, it is exactly opposite to the Kilonew-Fischer synthesis. Kilonew-Fischer synthesis, there is a lengthening of chain, means the number of carbon atom increases step by step by adding the suitable reagent. But here we exactly reverse, means here is a shortening of the carbon skeleton in this particular process, and that's why it is known as a rub degradation. Degradation means there is a decrease in the carbon atom. Suppose you have a starting compound is a, let us see, the most commonly used aldose is a what is that? Aldohexose. Aldohexose number of carbon atom, do you remember that? Aldohexose containing as a 6 number of carbon atom, and they are present in a carbon skeleton. Vertically it is written according to as a Fischer projection formula, and there is a certain rule according to as a Fischer projection formula how the bonds are written, that we will see later on. But here just remember how we can increase that. Let us take an example, that is a rub degradation. There are various methods of decreasing one carbon atom in the aldose sugar. One of these methods for shortening the carbon atom is the rub degradation. I already mentioned here, I already told you that rub degradation means there is a decrease in a carbon atom one by one, like that. From hexose we can get as a pentose, or from pentose we can get as a tetrose. Likewise, shortening of that carbon chain is known as a rub degradation, and this method start with the aldose, and hence in order to convert a ketose into the lower aldohexose, it is necessary to transform the ketose into an aldose. Ketose and the aldose, as we know that ketose clearly indicate that there is a carbonyl group is present. Aldose indicate that there is a here ketose means there is a ketonic group is present in that. Aldose means there is a aldehyde group is present in the organic compound, and therefore by from the these word ketose and aldose, they are clearly indicate that, or we can come to know that about the ketonic group and the aldehyde group. Ketose means there is a ketonic group is present, aldose means there is a aldehyde group is present. That you have to remember while studying, while altering, or while using these words. These words are gives the very clear cut idea what kind of the group were present in that organic compound, or in this particular case what we are talking, what we are discussing is a carbohydrate. And rub degradation in 1898 the scientist named that rub degradation. 1898 there is a what they did, there are the certain rules are there, or what we can call it as a certain steps over there for rub degradation. Remember first one, rub degradation. There is a first point to remember here, how we can decrease the one carbon atom, how we can convert the hexose into as a pentose. That means in a hexose there are the 6 carbon atoms, number of 6 carbon atoms are present. In a pentose there are 5 carbon atoms are there, and therefore 1 carbon atom is less, or what we can call it as we are shortening the bond length over there. And number 1, an aldose is oxidized by bromine water to the aldonic acid. What we are doing here in a rub degradation, first in an aldose, what an aldose is? An aldose is oxidized by, and aldose is oxidized by bromine water, and as we know that bromine water is a mild oxidizing reagent, and what it will do, bromine water to the aldonic acid. Suppose as we know that, let us see here, an aldose is oxidized by bromine water to the aldonic acid. Very simple procedure, very simple steps over here. Suppose we have a starting compound, let us see as a hexose, CHOH 4 times. For the sake of reaction condition, I am writing the structure over here. For suitability, C aldehyde group I am keeping at the top, then CHOH 4 times secondary alcoholic group present over there, and one is a primary. So this is as we know that it is a structure of glucose, mainly as a D-glucose. Why it is a D-glucose, that we will see shortly, but here remember this is a glucose when it is treated with bromine water H2O, we can write Br2 in presence of H2O, or bromine water, as we know that it is a mild oxidizing reagent. What it is? It is a mild oxidizing reagent, and what it will do, the mild oxidizing reagent will convert specifically the aldehyde group into the carboxylic group, and therefore you are going to get this compound COOH, then CHOH 4 times, and then CH2OH, like this. And this, the structure what we got, this is an aldonic acid, or we can call it as a gluconic acid. This is an aldonic acid, or you can call it as a gluconic acid, or it is a monocarboxylic acid. Mono means what? Single carboxylic groups are present in that carbohydrate, that is known as a monocarboxylic acid, and that's their role. This is the first step is taking place or generally used in rough degradation. Understood this one? Now let us move on to the second step. In the second, the aldonic acid is treated with calcium carbonate to form calcium aldonate, or that is a salt. What is happening over there? Now let me write here the second point, what we are going to do here in the next step. This is the aldonic acid we just now got over here. Now we are going to take this one, in a wording we can write the second point, an aldonic acid is treated with calcium carbonate. As we know that calcium carbonate, it is an base, and this is an acid, and acid and base were together react together, producing the salt of carboxylic acid, and the name of that salt is the calcium aldonate. So with calcium carbonate to form an aldonate means which is a salt, and calcium aldonate. Now here remember calcium aldonate, calcium aldonate means the salt. Any acid if you treat with base, the resulting compound obtained is known as a salt, as we know that. This is a general reaction takes place during when these two acid and base react together, they are generally producing as an acid, as a salt. Now this aldonic acid, as we know that we have already this one, this structure we are going to write as it is over here, COOH, then CHOH 4 times, and then CH2OH, and what we are going to treat with calcium carbonate, which is a base, and when it react with this, the resulting compound can be obtained is this one, can be obtained is here we can write COO minus over here, then CHOH, that 4 times as it is, then CH2OH, and then whole bracket, then twice calcium 2 plus plus you can write here 2 minus minus, or that type of the calcium aldonate or calcium gluconic salt is formed here, so which you can call it is a calcium aldonate, which is a salt form here, this one. And this salt, now in the third step what we are going to do over here, next one, this whichever the calcium aldonate salt is obtained right now over here, just now over here, this we are going to further treat with the suitable reagent. The name of that reagent is a Fenton's reagent. Remember, the calcium salt is then oxidized to yield oxidized by Fenton's reagent. Do you know the Fenton's reagent? Do you heard this word before? I think many of you might have heard this word, that is a Fenton's reagent. And the Fenton's reagent, which is the oxidizing reagent, which will oxidize, and what you are going to get over here to yield an aldose with one carbon atom less. So that is the main, for example, conversion of an aldohexose glucose into aldopentose, that is a ribose. How we are getting ribose, that we are generally seen over here. Now for the third point I am going to write over here so that you can clearly understood the rough degradation. So let us see the third point what I am going to mention over here. The calcium salt is there. The calcium salt is then treated with or then oxidized. The calcium salt is then oxidized by remember here Fenton's reagent. Fenton's reagent, and the reagent which I am going to mention, going to show over here, that is a H2O2 hydrogen peroxide and then Fe3 plus. That is this reagent is known as a Fenton's reagent because he discovered first time, and that's why name is given to that reagent is a Fenton's reagent to yield an aldose with an to yield an aldose with an aldose yield an aldose with one carbon atom less, right? And as we know that what is that, this COO minus then CHOH now is a 4 time here, and CH2OH here twice CH2 plus, and this reagent, that is a calcium salt, when we are using as a Fenton's reagent, observe this reaction carefully. Fenton's reagent and this is generally H2O2. Everybody knows that that is a hydrogen peroxide, and that Fe3 plus is a iron oxide, in a oxidation form Fe3 plus, and the resulting compound is formed as a CHO. Then remember here CHOH. Now here how many atoms are there? 4. Now one carbon atom is decreased. So here remember here only as a CHOH3 and then CH2OH. This is called as a pentose. This one is a pentose, or we can call it as a ribose here. Ribose. This is the structure which we got, and this is known as a rub degradation. Understood this rub degradation? What do you mean by the rub degradation? We have seen here very cleanly or very clearly how we can prepare this one. And aldohexose means generally we have taken as a name of that compound is glucose. Then we got as a aldonic acid. First one we treated that glucose with Br2 in presence of water, which is a mild oxidizing reagent which produce the aldonic acid or gluconic acid we can call it, and this gluconic acid further treated with calcium carbonate. Calcium carbonate is a base, and acid and base when react together they generally produce the salt, and that salt obtained is known as, that salt is a calcium salt or the aldonate. This is the compound which we got, and after that it is treated with Fenton's reagent, which is a very good reagent in presence of Fe3 plus, gives the aldopentose, that is a ribose over there. In this way we have what you can observe, or what kind of the conclusion we can draw from here. Generally there is a decrease in one carbon atom, or the shortening of the carbon skeleton in this particular process, and that's why the name is given to that process is a rub degradation. I think you generally knowing this, you might be understood what do you mean by the rub degradation. Three things you have to remember. First, what we are doing, Br2 in presence of water H2O. That is the first treatment you can treat over there. In the second, that you can treat with calcium carbonate, form as a calcium salt over there. In the third one you can use as a Fenton's reagent. Fenton's reagent generally as a H2O2 in presence of Fe3 plus. This is a reagent which can oxidize that salt into as a aldehyde group back again, but there is a one carbon atom is less. So this process is known as a rub degradation. These are the three main points you have to remember as far as rub degradation is concerned. Number first one, Br2 in presence of H2O. This is a mild oxidizing reagent. Whenever you are treating with this mild oxidizing reagent, it will suitably convert aldehyde group into as a carboxylic group, and whenever that carboxylic group is treated with calcium carbonate, it produce the salt, calcium salt is formed, and that calcium salt further treated with Fenton's reagent gives the aldehyde group back over there. So this process is known as a rub degradation. So now let us move on to the next point. What is the next point we are going to learn over there? Fischer projection and the perspective formula. Fischer projection and the perspective formula. So many of the time we have learned that point. So but let us discuss once again what is that Fischer projection and the perspective formula. Fischer projection and perspective formula. Perspective formula. Fischer projection and the perspective formula. That first one is a Fischer projection formula. First of all, let us consider over here, let us have Fischer projection formula. Fischer projection formula. Fischer projection formula over here. Now Fischer projection formula, here what? In the 19th century, German organic chemist Emil Fischer, remember, German organic chemist Emil Fischer introduced the use of projection formula for asymmetric molecule. Everybody knows that the asymmetric molecule means what? Or asymmetric carbon atom. Asymmetric carbon atom means what? The 4 different group attached to carbon atom is known as asymmetric carbon atom, or the other alternative word use or very specific word used for this asymmetric carbon atom is chiral center, and the asymmetric carbon atom one and the same thing, means both are the word using for this is the same. So Fischer projection formula, and in this representation let us remember certain point while writing or while applying the Fischer projection formula. Number first point is used or applied here is first one, the carbon chain is kept in a vertical position with one oxidizable group at the top. Whenever we are writing as a glucose, we are familiar with the glucose, so we are putting that aldehyde group, because glucose containing as a aldehyde group, according to as a Fischer projection formula, aldehyde group we are putting on the top, and rest of the carbon chain we are writing as usual. And point number 2, the horizontal bonds are considered to be projecting above the plane. So this is the second point, and the third point, the vertical bonds are considered to be projecting below the plane. This is the general certain rules, or the general rules while using the Fischer projection formula, or while representing the Fischer projection formula. Now is a perspective formula, or in this representation, in a perspective way, in this representation, the dashed or dotted lines indicate bonds extending behind the paper, and number 2, solid wedges or thick lines identify bonds standing in front of plane of the paper. So that is a general, and these two formula together with a simplified ball and stick model can be used to distinguish between the compound and its mirror image isomer as shown below. Let us see here ball and stick formula. Here similar to as here is I am showing here is a ball and stick formula. Suppose let us see here, and there are 4 group attached to carbon atom. As we know that carbon atom is a tetravalent in nature, and therefore here we can write here D, here A, then above side we can write B, D and E. That is the sake of convenience we can write. This is known as ball and stick model. Ball and stick model. This one. This is a very simplified way is shown A, B, D and E, 4 groups over there. And now Fischer projection formula. Fischer projection formula, simply carbon atom show over here, then A, B, D and E, that's it. This is the Fischer projection formula. Fischer projection formula. And now Fischer projection, this is a Fischer projection formula. And now the last one, which is a perspective formula. Perspective formula now is this group is generally shown by dotted line, and these are the thick lines over there. And now here A, D, B and the E you can write as it is. This is called as a perspective formula. This is known as a perspective formula. So in these are the representation of various, and now is a D-glyceraldehyde as a reference compound. As we know that from the beginning we are learning this one, D-glyceraldehyde. I don't want to use this word again and again, but it is a very important as far as carbohydrate chemistry is concerned. Glyceraldehyde as a reference compound. Always remember, in the study of carbohydrates we come across a number of optical isomers, and the simplest monosaccharide that possesses one asymmetric carbon atom has been chosen as the reference standard. For example, glyceraldehyde. An optical isomer, as we know that optical isomer means what? It can rotate the plane of polarization, means that compound is whether it is optically, these carbohydrates are generally optically active in nature. They can rotate the plane of polarization either right hand side or the left hand side, or dextro-rotatory or the leo-rotatory, and it exists in two optically active forms which are non-superimposable mirror images of each other, that is the enantiomers of each other. And as we know that enantiomer means what? They are the non-superimposable mirror images of each other. If you observe these two hands, they are exactly matching each other, but they are non-superimposable mirror images. Non-superimposable mirror images means what? We cannot use the, if you have a gloves, left hand and right hand, suppose this one is exactly identical, this is super, they are not exactly identical, they are not, this kind of the thing is known as a non-superimposable mirror images are known as a enantiomer. This is the simplest definition of the enantiomer. In enantiomer everything is the same. For example, or everything is the same, such as their melting point, boiling point, refractive indexes, physical properties as well as chemical properties are the same, but they differ in a rotation only. One is rotating, suppose as one enantiomer rotate the plane of polarization in a right hand side, another should rotate in a left hand side, and they are non-superimposable mirror images, and that are there. And these enantiomers of glyceraldehyde may be represented by Fischer projection formula, ball and stick model, as well as perspective formulas as follows. If you show as a Fischer projection formula, generally let us see as a glyceraldehyde, generally we are representing here very simply what, how do we represent this one? This is a carbon atom CHO, then here we are writing a hydrogen atom, here OH, and then CH2OH. This is a Fischer projection formula. If you keep here as a mirror, this one is a mirror. If you observe this structure, this is a glyceraldehyde. Which glyceraldehyde? Either it is a D-glyceraldehyde or the L-glyceraldehyde. Do you remember how many chiral centers are present over there? Can you recall? There are only one chiral centers are there. One chiral center, and therefore it is optically active in nature. And chiral center means what? The carbon atom carrying 4 different group is known as a chiral center, and therefore it is a chiral center. And if you look here, what do you get? HO. Then this CHO remains as it is. This also CH2OH. Only they are changing the position of hydroxy group and the hydrogen group, and rest of the thing remains as it is. Therefore, here look at this chiral center, and OH is present on the right hand side. Therefore, it is designated as a D configuration. This is a relative configuration, and this is shown by. Now look at here. Observe this structure. What do you see over here? The hydroxy group which is present on left hand side, therefore it is known as a L-glyceraldehyde. Glyceraldehyde, and therefore these are the in the same way we can represent, we can use ball and stick model, or we can use as a this one L-glyceraldehyde, and these are the relative configuration. Relative configuration, what does it mean? The configuration which is determined by comparing the configuration of the molecule with that of the some arbitrarily chosen reference molecule is known as relative configuration. The reference compound chosen was glyceraldehyde. The molecule is placed in such a way that the CHO group is at the top and all carbon are in a vertical chain. The configuration are assigned as follows. D configuration. The isomer in which the OH group attached to the chiral center is on the right hand side has assigned as a D configuration, whereas L configuration means what? The isomer in which the OH group attached to the chiral center is on the left hand side has assigned L configuration. And it should be remembered that a dextrorotatory compound may have dextrorotatory may have a D or L configuration. For example, D plus glyceraldehyde is oxidized to D minus glyceric acid. And now here there are D plus glyceraldehyde as well as D minus glyceride. Let us look at here when this L glyceraldehyde, when it is let us see, this is a D-glyceraldehyde, as we know that this is a D-glyceraldehyde. D-glyceraldehyde, when it is treated with what? When it is treated with or oxidize it, what is going to happen? This aldehyde group is going to convert into as a COH, then here OH. Now yes, this is a OH as it is H, and this CH2OH remains as it is. But if you observe, if you determine its optical activity, what you are going to get here? The optical activity is shown by plus dextrorotatory, this one, and now this D minus glyceraldehyde. Minus glyceraldehyde is over there, and therefore here look at here plus and minus dextrorotatory and the levorotatory does not affect, means there is no change in that, means the D and that plus and minus does not correlate to each other, means that D may have plus and minus rotation, optical rotation. Similarly, L can rotate the plane of polarization in right hand side as well as in a left hand side, means they are the experimental quantities. Therefore and this D and L are the relative configuration, and the experimental properties are totally different, and therefore they are the different one. Then absolute configuration, and as we know that in absolute configuration, similar to as a R and S configuration, we already talked many times about that. But let us see, here is a glucose. How many chiral carbon atoms are present in the glucose? There are 4 chiral carbon atoms. According to as a Wand's rule, 2 raised to n means 2 raised to 4 is equal to 16. 16 different isomer are possible, and glucose is one of them. So I think with this, let us stop today here. Remaining we will see in the next lecture. Thank you. Have a nice day.